All right. So it follows up nicely with Christopher, in that now that you know all the elements from the MATLAB interface with Gadgetron, we thought it would be nice to drive you through a do-it-yourself project where you start your own MATLAB project from examples that are provided by Christopher. And so we're going to focus on one simple example, that is the MP2 Rage, which is a turbo flash. There's two turbo flash echoes, train of echoes, that are required after a single inversion. Oops. And we're going to try to reconstruct these two images, as well as to reconstruct the MP2 Rage image. So trying to get a secondary image out of the basic images and send them back to the client. All right. So I'm going to have, just like Christopher did, but I'm on Windows, three shells. The first one is going to be the Gadgetron server. The second one is going to be the Gadgetron client. It will serve as a client. And the third one will help me just pull up the viewer. And I'm going to have MATLAB. And we're going to start from the examples. All right, so I have installed the Gadgetron MATLAB package from the add-on right here. And then we have the examples, and I created a custom folder so that it will be seen by MATLAB anywhere. And then from this, in this custom folder, we're going to create our own custom reconstruction for the MP2 Rage. We're going to work on the buffer recon. So we're going to start from buffer, just like Christopher did on the recon data, which is also called buffer. So we're going to copy that buffer recon and paste it into custom. We're going to copy and paste also the steps. And then we're going to modify them as we need. And so paste, right? And so just to review the to-do list that we have a to-do list of 3 points. We need to handle complex images all the way out. So far, Christopher has shown only magnitude images coming out. We need to keep complex images all the way out to process them into this computation. All right. So we need to continually process complex images, send them out. We need also to manage buffer dimensions. In the examples, the buffer is handled, but the dimensions extra beyond the X, Y, Z and the channels are not handled. So we're going to see that and see the solution for that. And then finally, we need to combine the different echo images into an MP2 Rage image and then send it down to the client as well. So let's start from the config file. So the config file is provided in the solution on the GitHub, but it has basic steps that are, apart from the reader and the writer, there's a noise adjust gadget that is provided by Gadgetron, the remover sampling gadget, some compression, just to keep the volume of data a little bit lower, and then acquisition accumulate trigger that triggers on repetitions. It will not trigger because there's no multiple repetitions in our data set. It will only trigger once. And then the bucket to buffer, it will create a single data set that combines all the contrast, that is the two different TIs or echoes of the MP2 Rage, and an average if we had any other average. And then we're going to send it down to MATLAB through a script, a function that what we'll call MP2 Rage buffer recon, that is based on the buffer recon provided for the examples. All right. So back to MATLAB, we copied the buffer recon into the custom folder, and then we're going to change the name of that function. And then we can also change the name. Okay, and now we have different steps. The basic reconstruction, they create slice from recon data that bundles all of the data, and then we combine the channels. We create the image and then we set it down. The part where it starts to become magnitude is when we combine different channels. Up to this point, images are complex or data are complex. And at this point, we need to modify these steps. Okay, so we're going to use our custom functions so that we don't interfere with the examples. And then if we don't modify them, we can revert back to the regular examples. but just to make sure that we don't interfere, let's use all the constant functions. And then, like I said, the key point is that in the custom steps, the channel combination is done in a magnitude way, this way. So we want to keep that as complex all the way up. So we're gonna keep the magnitude, as it is. Okay. So we're gonna copy that up, and then we're gonna try to get the phase. And we're gonna do a simple sum of the image data phase, which is angle in MATLAB, multiplied by the image, the apps values, the magnitude of these images of each channel. Okay. And then we're going to divide that by image apps. And then we sum over channel 1 because, as Christopher said, the convention is that the channel dimension is the first one. And then the image data eventually would be image apps times the phase. Okay. And so now we will output data that are complex and not any more magnitude. And so we'll put it down into the chain. And so up to this point now, because we use, oh, did I change the wrong one? We use our custom, I think I changed the, sorry, and buffer and recall. And because we use our custom functions, we will output complex images. I'll manage to write. Okay, so we can now combine channels into a complex way, but we still need to create complex images as well. So we're gonna open this function and see that it outputs magnitude images here. But we want complex images to be able to process them down into the pipeline. So one way is to simply just change that or on purpose. There's a smarter way in the solution that handles depending on if the images are complex or real to output magnitude of complex. You can check that in GitHub. And so with that, we can process the images by calling the Gadgetron custom and then the buffer recon. And then I have a data set of a simple 2D, not this one. I have a data set of a simple 2D MP2 range that I will output in output 1, calling the buffer MP2 range recon. It will call Gadgetron, it will call MATLAB, and then MATLAB will process accordingly to output an image. I think it's finished. And if I call the viewer and then open the file, there's the out one. And then this one has one image. The one thing is that I have two images in this data set, but only one is output. It's because the buffer dimensions are not handled properly by the examples. So another step, if you wanted to start from the examples and make your own reconstruction, is to handle the different dimensions. So let's go back to MATLAB. And then the way we create images needs to be changed. And so we want to create images on other dimensions. So we start with initializing the dimension counters. These are N and S in Gadgetron convention. And we're going to loop over N and S that are the extra dimensions that are defined in the configuration file. So if you look at the configuration file, there's an N and an S dimension, this is contrast and average, and we need to loop over these dimensions. So if we go back to MATLAB, we can just loop over, and we can define first the dimension size, which is the size of the image that is coming down, and then we can loop over. and then we can just loop over n and s, and if we do that, we will not change the data nor the reference. So we need to consider the dimensions that are the extra dimensions of n and s, which is dimension 5 and 6 in the data set, and the image reference as well, that is provided as an array. Okay. And now we will loop over the dimensions n and s, and then output multiple images. Okay, we might want to initialize this structure, and we can do that with the Gadgetron types. Just to make sure that we start from the correct image type. And it will initialize with an empty array, and then we will grow as images come down. Okay, if we do that now, and we recall our same reconstruction, again, the Gadgetron client is sent to the server is calling MATLAB. And now it's done, finished. And if we reopen the same file, there's new images, and then should be multiple ones. I guess I didn't make something correct. Anyway, I have I'm wrong at the size. It's the size of the reference that should be output. We do it again. I don't have a very fast computer, so just shows you how that works. And then the computation is finished. And then I haven't closed it. So if I reopen it, same. It wasn't. Is it finished? Yeah. I guess I should close it and then reopen it. Okay. Uh-oh, I have items issue. No, it doesn't want to open. There. Unable to open file signature. I should have closed it maybe. If I start from again with another file. Oh, a lot of errors here. Yeah, it's because you couldn't create the file because it was already in use. Okay. Okay, now it's done. Open it. And then this one will have multiple images. Okay, so we did two things here. One, we changed the combination of channels to handle complex data. And then two, we managed to loop over the dimensions of the buffer to account for multiple dimensions, that is contrast and average in our case, and output complex images down to the streamline. If you output images that are complex, just pay attention that the XML configuration file has to include an extract gadget to extract the magnitude out of these complex images down to the streamline. Otherwise, the client will probably not be able to read them. It will still save, but you're not able to open them in ISMRD viewer or on any scanner. Okay. So we have now in our process, we have created complex data through complex combination of channels. We have created complex images, and now we need to create an MP2H image. Okay, so we're gonna call a new function, just like Christopher showed, that we'll call steps and then mp2rage equals combination. And we can just call next again. So the same way here, we are calling functions over function handles. And then we're going to consume next as the last one. And then once we have created this image, we still need to send it. So we're going to send it again. Okay, so we will send images twice. Once the raw images, and then once the combined image once it is processed. So we're going to create that function. And then in terms of time, I will just get it back from my backup because it's just rather long stuff. And then I change the name. It's called combine echoes. Okay. And if we open that one, what it does is that it receives complex images. It will use the first one as a template just to make sure that we keep all the headers correct. And then it will compute just to make sure that the screen shows all the computation. It will compute the formula that is provided by the MP2Rage paper, this formula right here. So back in MATLAB, we'll compute that formula, and we just have a multiple factor just to account for the scaling of these images. And then the image will be back to complex because we output complex images now. And then we update the series index just to make sure that they don't overlap with the other images. Okay, so we compute the MP2Rage image. We just add an empty, very small complex part, or we could just have called complex in that. And then we update the image series just to increment and make sure that it doesn't overlap. We include that in our buffer recon, and then we send it down as next is called over and over and over again. Okay, so this is how you can just chain up functional handles with images as a first step and then processing as a second step. Okay, and so if we go back to the client, and then we call the same configuration file again, but we will call a new, we'll create a new output file. It goes into Gadgetron that calls MATLAB. It takes a little bit of time to do the magic. Okay, it has sent images to the client. It has sent 3 images to the client this time, sending images to client 1, 2, and 3. And if we try to open it, I can close the previous one. Okay. And if we open that, 3, okay, it's open. It has 2 series, the images, the 2 images that were from the raw images, and then it has a sequence series that looks like a little bit like a map. It's not yet a map, but it's a processed image. And so they will not overlap because there's 2 series. So if you take that to the scanner, you will also see 2 series in your folder, in your patient folder. Okay. Just to be a little more detailed, I skipped a few things because when you have to loop over dimensions for this purpose, so we looped over N and S to create different images, complex images. We also have to loop a little bit over different steps, like the create slice that also has a loop that was not provided in the examples. But you can find that in the solution in the GitHub of the class. It loops over the dimensions N and S, and then it just retrieves the data that are dimensions 4, 1, 2, 5, 1, 2, 3, 5, 6. Again, channel is dimension 4 and comes as first. And then it has a struct fun, like Christopher showed, that outputs the buffer headers in a non-uniform output. And this just loop, that's why the reference is a structure now of references. you need to do that. And then when you send images as well, if you look at the send image, it also needs to loop. It's not in examples that are provided with the Gadgetron toolbox, but it's very easy to loop over the dimensions of the images and just send it over and over. Okay. I didn't do that in terms of because of time, but it's not so complicated to do. Okay, so we've achieved our task of computing the reconstruction of the MP2H images and then computing an image, an additional image that is the MP2H image. Okay, we did the complex image all the way out. We managed the buffer dimensions, and then we combined the echoes into a single image and send. Now, if we review, well, let me go back to full screen. If we review the different types in Gadgetron, like Christopher quickly touched on, there are 5 types that are available in Gadgetron MATLAB. The acquisition, the bucket, the buffer, or the recon data, as Christopher showed. The image array and the image. Each follows a different step, but only 2 types can be outputted, the acquisition type and the image type. In Python, it's not the case. In Python, you can output all of these types. But in MATLAB, you can only input them. The different applications that we could thought of for the different justification of the use of each is that you can get acquisitions in and out for applications like self-gating or adding a trajectory for non-Cartesian sampling, or you could just use view sharing as well and send acquisitions as different bundles of different sizes. The bucket is very useful for sparse matrices where a lot of lines are not sampled. So instead of having the buffer combine all the empty lines, the bucket will not do that and will be faster to provide all the data in non-Cartesian acquisition or sparse matrices or Cartesian acquisitions. The image array is a structure that contains all the images that are reconstructed. It's very useful for signal and image processing, such as mapping, but it cannot be output. You will have to handle the output of all the images. And then finally, the image type can be input and output in MATLAB. It's very useful for segmenting or masking the images, but it also is useful for image processing. Of note, these objects contain multiple sub-objects that can be passed on and used at different steps, just like the waveforms, the metadata, trajectory, and density of compensation. Okay, and if we review our MP2H, the purpose of the MP2H was simply to process the images and output the MP2H extra data. So just to review a config file, we can output an input acquisition with MATLAB, that is at the step before the acquisition accumulate trigger. We can input buckets. We can input buffer. We can, did I lose my cursor? We can input image array, and we can input and output images. The example for the MP2H that we just completed was this step, going from buffer to image, which is a short application. You could start from bucket. You could start from acquisition directly. But really what we wanted is to have an image processing step. So we could have just done the image to image processing. So we'll just cover that as well as a final step. Okay. So just to review the config file that we need to do, we have a standard config file that just performs the usual steps that are removing oversampling, the accumulate trigger, bucket to buffer, a simple reconstruction, the image array that is split into different images. And then at this stage, we can insert a MATLAB gadget that will combine the images and extract all the images down to the client. Okay. And so if we go back to MATLAB, we need to create a new function here in our custom. And I will use my backup just to keep the time short. It will combine all the images. And if we look at the function, it has to be a function handle just to be consumed again, because we want to keep the use of Gadgetron consume. And so we're going to use an accumulation of the images that are coming through. if we look at the config file, the image array will be split by this gadget, and all images will come one by one to MATLAB. So we want to accumulate them so that we can process them. So back to the accumulate function in MATLAB, we will accumulate images that are coming through by the connection next, and we will store them in a function that is called just all images. It has been initialized to an image type, but empty. And we just keep a counter just to keep track of the images that are received. So we accumulate images into a structure, and we send them immediately just to make sure that the images are untouched and can be passed down to the line and received by the client. But what we're interested in is that at the stage where we've received all the images we need, in our case, just 2, it's very easy. So if the counter reaches 2, we want to compute the MP2H. So we'll compute the MP2H image with this function that is written down there. Okay, it's the same as before. It has a multiple factor just for scaling, and then the computation of the MP2H image. Simple. And then we make it complex again for the extract gadget to work, and we increment the series number again, just like we did. We can do it in a smarter way where we get the image series index of the initial image and just increment it here. Okay, and then we will send it down to the pipeline by connection set. And so if we perform that reconstruction, so we will, not this one. We will call again our clients on the same data set, but this time we will output a new data file. And instead of calling external MATLAB buffer, we want to call our image pipeline. So we'll do that. We go back to Gadgetron. It has started calling MATLAB. This time, Gadgetron will do all the computation, but the image processing. So it receives, it's actually faster if you do it all in C++ gadgets than sometimes in MATLAB. It's not necessarily the case, but this is the case here. And we received one image, and last image shows the protocol name. Okay. And if we do that, hopefully it will have output the different images. So it has received the different series, okay? And it has also processed the images to output a new series, just like we did before, but this time doing only the image processing in MATLAB and not everything else that was done before by the Gadgetron gadgets. This is a good example of how you can leverage Gadgetron power to do only the steps that you need, and in this case, image processing. Usually Gadgetron is not an image processing framework, but in this case, it's a good example of how to change a little bit that to make it for your own project. With that, I completed the task that we set in 2 ways. One way was to complete from buffer to image, and another way was to do an image processing only reconstruction. I'm done. Thank you for your attention. And I pass on the hand to Aurélien. I need to stop sharing my screen. Your turn. Is there any question first, or we'll answer a question later, maybe?
Okay. Does it work? Is it working?
Yes.
Okay. So for the next part of the talk, we'll present a way to reconstruct 2D non-Cartesian data. So the data are shared in a new Zenodo on this new Zenodo folder, I guess. No, it's already available on the first one. So it's in day 3, example spiral 2D, and we will reconstruct the spiral 2D SSFP.H5 datasets. So it is a 2D spiral dataset that Raj sent me, and I was not really aware of what was inside. So it would be a good example to take a look at what is inside the data. Okay. So like always, we'll have, so I have opened MATLAB somewhere. I have my Gadgetron server run, and for the client part, I will use just a bash script to be faster, to go faster, and it is just this command line here. Okay, so I will, as input, I will use my dataset. I will output this dataset, and I will use this config file demo2 noncart.xml. Okay, so let's have a look at that. So first part is the XML part, of course. So it's you are used to it, I think. So you have the reader and writer, and after that, I will use all the standard steps: noise adjust, remove oversampling. I will call compress the data to only 4 channels, and then you can have multiple possibilities. So here I decided to use the acquisition accumulate trigger gadget to obtain a bucket, and also to use the bucket buffer. So the bucket buffer is kind of weird because it will not output a cascade like with Cartesian data. Here we'll get something with only which will look like the bucket. We'll see that later. And then I will just send the data back to MATLAB. Okay. So the first step is to take a look at the data. So we'll just create. Okay, here. I will just create an empty function that I will call with Gadgetron. Let's do that. You can just remove this part for now and resolve it. Okay. And we call that, I don't know, maybe this. We can store that under my folder. Okay. So if I want to launch my script, I have to call, to use this line, to put MATLAB into listen mode, waiting to call this function that I just created. And we have also to put, we will also put a breakpoint to stop the data, to stop MATLAB into debug mode. So now I can launch the construction. I will just okay. So now we are stuck at this point, and I can have a look at the data. So in the acquisition, you have the buffer and the reference is empty. And in the reference, you can see that we have the data sets and the trajectory. We have the trajectory because it's a non-Cartesian data set, and we need that to do the reconstruction with the grading algorithm. So for the data set, let's maybe, okay. Have a look at the side of data. So this, the first dimension is the readout size. It's pretty long because it's a spiral readout. we have 48 interleaves, and we have the 4 channels here. Okay. If I take a look at the trajectory, weirdly, we have 3 dimensions. You can see that. So 3 dimension here, the readout dimension, and the interleaves dimension. So it's kind of weird that we have 3 dimensions here, and we can try to investigate that. So let's go back to this. So what we can do is just plotting. So what we have to do to have is only 2 dimensions for kx and ky that trajectory, and here we have another dimension. So if I just take that part, will show that. So what I will do is plotting the trajectory, the first 2 dimensions of the trajectory together, because I think it is the kx and ky, and the last part also. So it might be that, but okay. So 1, 2, and 3 for the second subplot. Let's plot that. And if I do that, okay, so the first 2 dimensions is the trajectory. And this one, it is something called the density compensation function. It is used during the grading process to compensate the fact that we oversample the center of the K-space, because each readout will fill the central part a lot. Okay. Normally, we should have this density function into the field density of the buffer of the recon data object. So let's see that. But here it is empty. Okay. So we can fill it either by hand with MATLAB, or what we can do here is create a new reader to directly separate the trajectory from the density during the reading of the data. One minor question is why do we have this density compensation along the density? It is because it was a way to do that a long time ago in the MATLAB Live, Gadgetron Live, and it is still in Gadgetron. So if you check at some gadget, for example, this one. So if you take a look at the gadget grading recon gadget base, you can see that there is a special function called separate traj and DCW that will just separate the trajectory and data if we saw that there is 3 dimensions along the trajectory. So we want to remove these aspects in MATLAB, and to do so, we will change the way we read the data. So I will directly switch to my example, my function. So what we want to do is just change the way we read the recon data. There is a function, thanks to Christopher, to do that. So we just call this function and say, okay, I want to change the way the recon data are used. We can are read. We can also change that, for example, if we want to change the way the acquisition data is read and stuff like that. And we'll change the function by a new function that we define. So we can look at this data. And yeah. So for this data, the only modification I made is that at this step, So I take the standard reader and just change some part of it. So the only step I change is this one. I say, okay, I want to separate the trash and the density for the buffer, but also for the reference. Here we don't have reference data, but if we have them, we have to do this. And I create a new function that does that. Okay. And now if I, so in my function, I will just say, okay, change the way I read the broken data by this new method. Okay. Let's just kill this MATLAB for now. And I will rerun this with my, I will rerun the reconstruction with my function, with the header added. Okay. I will put a breakpoint just after the acquisition, next acquisition, like I did on this function. And if I run the reconstruction now, let's do this again. Okay, so it stopped at this step, and I can have a look at the acquisition. And now we have the trajectory with only 2 dimensions, and the density is filled also. Okay. So for the next part of this talk, so now we have the trajectory and the data and also the density, and we want to do the grading reconstruction. There's a lot of possibilities to do that. Either you can use your own MATLAB code if you want, or here I decided to use the BART toolbox because it is a well-known yes, it is a toolbox that is used a lot in the MRI community, and it is very useful, mostly for compressed sensing reconstruction, but there is also a lot of non-Cartesian reconstruction possibilities inside. Okay, so let's just put that. So the first step is to reshape the data accordingly to BART. So BART wants the trajectory to be of this size. So BART requires three dimensions for X, Y, and Z. The readout and the projection. So for us, it is interleaved. Because we are in 2D, we will fill the last dimension with only 0 inside. So I will take our trajectory in trash 10. Like that. I will create an empty trajectory with the good side. And I will just put our trash 10, so our trajectory, inside the first 2 dimensions, to fill the first 2 dimensions. And we also have to scale the data accordingly, because for this trajectory, see, I think the maximum of this trajectory is 0.5. Let's see. Okay, 0.5. So the trajectory is defined with from minus 0.5 to plus 0.5, and BART wants the trajectory to be in scaling with the scaling. So we just need to multiply this by the matrix size along the X and Y matrix, because it's the same area. So we just do the multiplication. For that, I need, of course, this information, so I can get it from the header. So I will get the matrix size along the X dimension. After that, I also have to reshape the K-space data. So for BART, we need the first dimension to be 1. Then we have the readout, the interleaves, and the channel after that. So we'll buffer the data into a matrix. I will take a look at the dimensions, so the readout, the number of interleave, and the number of channel, and then I will reshape the data accordingly. So now matrix has this side, 1, the readout, interleaves, and channel. Okay. And in order to be able to use the density compensation function, I have to replicate the density compensation function accordingly to the number of channels. So for now, the DCF is, let's see, is size of the density is this, and after using the RepMap function, I will duplicate that dimension by 4. Okay, and it is exactly the same size as the matrix. It's important because I will use that later. Okay, so now we can use bar directly. So for in MATLAB, you can call BART like that. So we will use a function BART that will call BART outside, and we'll pass the functions that we want to use and the arguments. So here we'll call the new FFT function with the option -a, which means that we will do the standard grading. Okay, and after that I will do the root sum of square with BART. I also could have used the function shown by Stanislas and Christopher, but I wanted to show that we can do a lot of things also with BART. And then I will plot the results. Okay. So it looks like that. It is very blurry, and it is normal because it is a standard grading reconstruction, and we have oversampled the central part of the K-space, so it is low resolution. So we have this blurred image. If we want to compensate that for non-Cartesian acquisition, we just have to multiply the matrix by the DCF. And if we do that, we will obtain this image now. Okay, I'm happy I'm able to do the proper reconstruction, but we need the density. So the question is how it is calculate the density. So for radial acquisition, we can do that analytically, for example, and even for some standard trajectory. But if you want to work with a more complex trajectory, you have to use some dedicated algorithm. You can find one on the MRI Unbound site of the ISMRM. But another option is just to use iterative reconstructions that will correct that. And you have this option under BART, and you can just say, okay, you want to use the -e option that will perform the iterative reconstruction. So of course it's longer to do this kind of reconstruction, but the results will be the same. And in terms, so here, with the inverse, it's globally the same results, and it's even It's supposed to be better with the inverse, but it takes longer to reconstruct the images due to the iterative aspect. Okay, so now you are able to reconstruct non-Cartesian data easily with using BART. Just for you, I also put some advanced method. So, for example, if you want to use the compressed sensing aspects of the compressed sensing function of BART, you need to do something first, is to calculate the coil map sensitivity. So there is multiple ways to do that. I put the first one and the second one here. So the first one is just to, okay, I will grid the data, regrid the data first. And after that, I will go back to the cast space because it is an image like that. I can go back to the cast space and then use the eCalib function, which take as input a cast space and give back a sensitivity color map. This works well. Let's see that. We can also have a look at the sensitivity map if you want. Let's see. So it will look like that. So I have 4 channels. So, and I can use that after to do the proper, let's see, to do the parallel imaging compressed sensing reconstruction. So if you need more information about this line, you can go to the MRI Recon community, and there is a webinar which explains what happens. So mostly we say, okay, I want 200 iteration, and I want to use a regularization with a wavelet transform along the first 2 dimensions. It is a bit mask, and with this value for regularization. And also I have to input -t. So -t says, okay, I want to do non-Cartesian reconstruction, and I have to input the trajectory, the matrix size, the matrix data, and the sensitivity. Okay. So if I use that, so it may take some time because I have to do the reconstruction. Okay, so let's see. And I can plot the results here. Okay, so now I have the adjoint plus density, the inverse, and the peaks. So because it is a fully spiral data set, I don't have a lot of effects. We don't see a lot of effects using the peaks, but I can degrade the quality of the image if I put the wrong regularization value, for example. One other method that has been implemented during the next months, I think, is to directly use the NLIV method. So it will, as always, we'll enter the matrix and the trajectory, and this kind of function will directly perform the reconstruction and also output the sensitivity. Okay. Because the grading part of this algorithm is doing the grading on it will increase the size of the matrix during the grading part. I have to crop that in order to use that for the peaks reconstruction. So we can check the sensitivity. Let's see. It's not exactly the same results because it's not the same algorithm. And I can reconstruct the data sets the same way. So except that I will use this sensitivity map. So you have to figure out what is the best way, what is the best results for your application. And that's why it's important to be able with MATLAB to do all this prototyping. After that, I want to send back the data to Gadgetron. So you already saw that. So I will create a new image with the data and with the reference header. And I will say that it is a magnitude dataset. And it is magnitude dataset because I keep them, I store them into the image to send into this into image to send. But first we take the absolute value and we permute accordingly to the old Christopher way of storing the image. And we can send the data. Okay, let's do that. So if I want to take a look at the data, I can use the instrument viewer. Let's do that. Let's go to start, and it is done. So you can see that there is a lot of images. It's because I overwrite the dataset inside this file. Okay, so for today it will be this one, I guess. Okay, so I only send 2 images, and we have a scaling. The scaling of the images are different. That's why we have this issue on the images, but it is just a scaling issue. Okay. I think that's all for my presentation. Let's just look at that. Yeah, okay. I also put the function to read directly the data under MATLAB, because maybe you want to stay in MATLAB to take a look at the data in H5. And for the conclusion, here we use the BART toolbox, but of course you have access to a lot of different other way to reconstruct non-Cartesian data. So I put some of them here. So that's it for me. Minor things to say. In this lecture folder, we also put an exercise at the end. So the objective is also to reconstruct the 2D MP2H dataset, but this time we don't want you to use a bucket to buffer gadget. So you have to buffer the data under MATLAB. Just a little hint, you can use linear indexing of MATLAB, it will be faster. And we put the correction and detail instruction in this folder if you want to look at it later. Okay, so you can work on that before the next week, and you can ask some questions on the Slack channel if you have some trouble. Thank you.
Thanks, Stanislas and Aurélien, for the presentation. I have a few things to mention. So Stan and Aurélien also, in their tutorial, they made some, they had some content on nested function in MATLAB. You can share your screen, Aurélien or Stan, as you wish, and to show what you, and you also give some advice to use MATLAB on Windows with WSL for the Ubuntu part. So it's content that can be useful for you. And
so you said about nested functions, and what about WSL?
Yeah, in your tutorial on the
yes.
Gadgetron Online Class, you put some content. And
yes. right here.
Yeah,
If you
just
go
to
into-
mention to everyone that it's available, and
yeah, there's a lot of content that is not covered during the live talks, but there's an introduction about packages and nested functions. The data type we covered. How to distinguish between pass-through and basic stuff that Christopher covered. And the demos are almost all covered, but not all of them. The buffer step was not done, but it's there for homework. Also,
okay. Thanks a lot, Stanislas, for that. And also, I would like to just ask David Hansen to say a few words, because Aurélien so present to us how to use BART in the Gadgetron. So this is really useful for going fast. I mean, when you do kind of exotic reconstruction, but the Gadgetron include so lots of tools for doing fast reconstruction as a radial or spiral. So I will just, David, let's say a few words about it.
Sure. Well, Gadgetron has, we have non-Cartesian sens and non-Cartesian compressed sensing reconstructions available on the GPU. There are gadgets for those. Some of them have been used for the real-time stuff we talked about in the first week, but there's also CPU gridding. Hopefully next week I'll be able to show you CPU non-Cartesian sens, but there aren't gadgets available for that right now. They're just toolboxes inside Gadgetron, so you'd have to write a lot of C++ to use them. So if you're on CPU, you're stuck with gridding. In GPU, we have more advanced options ready to go for both spiral and radial trajectories.